Now we remarked earlier that the dimensionality of the vector space is determined by the number of alternatives in the Stern-Gerlach type experiments. Okay, so if you want to describe the spin of a quantum mechanical system, for example, electron, all right, if you want to describe the spin of an electron, the complex vector space that we have to use is simply two-dimensional. That's the simplest thing that we can do in quantum mechanics. Right? If you are talking only about the spin, you can use a two-dimensional vector space. Why? The dimensionality of the vector space is determined by the number of possible measurement outcomes or number of different things that the electron can do. In the case of spin, if you're measuring spin, there are only two possible outcomes. It's plus h cross by 2 or minus h cross by 2. So correspondingly, the dimensionality of the complex vector space to describe such things should be two-dimensional. Right? Now, if an observable has capital N possible measurement results, then we should talk about an n-dimensional vector space. Right? If there are n possible measurement results, we should talk about an n-dimensional vector space. That's just the generalization of the spin case. In other words, we would be talking about an n-dimensional vector space spanned by the n eigenkets of observable A. Now, this is a little bit difficult to grasp at the moment, but we'll see that this works. All right. So, in other words, we would be talking about an n-dimensional vector space spanned by the n eigenkets of observable A. All right. So, suppose I'll try to explain this. Suppose corresponding to observable A, we have got n measurement outcomes. And let's say 3, for example. Let's say that there are 3 measurement outcomes. The 3 measurement outcomes are A prime, A double prime, and A triple prime. These are the 3 possible measurement outcomes of operator A. All right. Now, there are 3 alternatives. So, we should use a 3-dimensional vector space to describe everything related to this particular observable. All right. Now, in this 3-dimensional vector space, we know that corresponding to the measured value A prime, there is a ket or the eigenket ket A prime. Corresponding to this, there is an eigenket ket A double prime. Corresponding to this, there is an eigenket ket A triple prime. Okay. All right. Now, we will be actually talking about all possible linear combinations of these 3 eigenkets. We'll be talking about all possible combinations of these 3 eigenkets. Okay. For example, we could talk about states like this: alpha is equal to C1 A prime plus C2 A double prime ket, okay, plus C3 get A triple prime, etc. This is the dimensionality of our vector space. The state could be ket A prime, ket A double prime, or ket A triple prime. It could also be any linear combination of these 3 kets. Okay. All right. The set of all linear combinations of the eigenkets of observable A is called the span of the eigenkets. Okay, the set of all linear combinations of the eigenkets of a particular observable is called the span of the eigenkets. That's just a technical term we'll be using later on. This will be called the span of the eigenkets. I will try to understand this by an example from two-dimensional real vector space. Now we can consider two. For simplicity, let's say that we are talking about two orthogonal unit vectors. All right, in a two-dimensional plane. Consider two orthogonal unit vectors x hat and y hat in a two-dimensional plane. This is just an example, a familiar example that helps us understand these things. Then any point in the plane can be reached by scaling and adding these two unit vectors. This we already know, because any point in the plane can be represented by two numbers, 2, 3, something like that. Right? This means that we can draw vectors to any point given by 2, let's say 2x hat plus 3y hat, etc. like that. Okay, so we can reach any point on this plane by scaling and adding these two unit vectors. All right, so if any vector, basically any vector that you can draw in a two-dimensional plane, can be represented as linear combination of ax and linear combination of x hat and y hat. All right, so any vector in the two-dimensional plane can be written as a linear combination of these two vectors. All right, then we say that all points in such a two-dimensional plane can be called span of the vectors x hat and y hat. Right? So this two-dimensional space, two-dimensional plane can be called the span of the vectors x hat and y hat. Okay, and we know that we call this x hat and y hat as base vectors. And if you have the base vectors, a complete set of base vectors, any vector in that space can be written as a linear combination of these base vectors. Right? So basically what we are saying is that eigenkets have, they are like base kets. Okay? They are basically base vectors. Eigenvectors are basically base vectors. Okay? So the idea is that once you define your complex vector space, any vector in that space can be written as a linear combination of all the eigenkets. Okay? So this will make these things more concrete and will maybe prove some of these things as we move on. All right. So just like this, all right, just in this, just as we call x and y as the base kits, okay, the eigenvectors of a particular operator, for example, an n-dimensional vector space, there would be n eigenkits, okay, and these eigenkits will form base vectors. We'll see that these will form base vectors, and any vector can be represented as a linear combination of the eigenkits of an operator. Okay. Now these things may seem a little bit arbitrary at the moment, but don't worry, all right? We'll make all these things concrete as we move on, all right? We'll make things more clear as we move on. And this means that an arbitrary ket alpha in the space, that is the span of the eigenkets. Okay, we said that if you are talking about the observable A, which has n eigenkets or n possible eigenvalues, this means that there are n possible measurement outcomes. Then we have to use an n-dimensional vector space. We have to use an n-dimensional vector space, and this n-dimensional vector space is the span of the n eigenkets of A. This means that once you define an n-dimensional vector space, we can represent any vector in that space or any physical state as a linear combination of all these n eigenkets. In other words, these n eigenkets form a base set of base vectors for our space. Okay, these n eigenkets form a set of base vectors for the relevant complex space in question. Right? This is what we mean when we write alpha is equal to sum over a prime c a prime get a prime. This simply means c1 get a1 plus c2 get a2, okay, plus c3 get a3, etc. up to cn get an. This is the meaning of this thing. Right? Any vector can be written as a linear combination of these things, or we say that the n eigenkets of the operator A form a set of base vectors, Okay, n eigenkets of operator A form a base ket. Right? Now, if you're listening really carefully, you might have some doubt, right? Because we said that we could choose two directions, x hat and y hat, two unit vectors as base vectors. Okay, but these base vectors are not unique, right? These base vectors are not unique. You could as well choose unit vectors along two different directions as the base vectors. Right? You are allowed to do so. You could use x prime and y prime as base vectors, and then you could expand any vector. You could write any vector in the same space as a linear combination of x prime and y prime also. This you are allowed to do. So we know that in the case of real vector space, the choice of base is not unique. The choice of base is not unique. All right. In the same way, this expansion is not unique. The choice of base is not unique, but we'll see this later. Right? We'll see this later. The basic idea is that A is not the only operator that we are talking about. There could be other operators corresponding to other observables like B, C, etc. Okay, and we'll see that generally you could choose either the eigenkets of A or the eigenkets of B or the eigenkets of C as the base vectors. Right? So the choice of this base is not unique. This expansion is not unique. Right? And all our predictions and all this quantum mechanics depends on crucially on such expressions. Right? So we'll look into these things in quite some detail. Now, the question of the uniqueness of such an expansion will be postponed until we prove the orthogonality of eigenkets. Okay. All right. Now, let me try to explain these things in the case of the Stern-Gerlach experiment. All right. In the case of the Stern-Gerlach experiment, we had the operator Sz. All right. Now, Sz, we said that there are two possible measurement outcomes, plus h cross by 2 and minus h cross by 2. The corresponding states we called sz plus, get sz plus and get sz minus. Okay, you might have already guessed that this sz plus and sz minus form a set of base vectors. They form a set of base vectors, which means that any vector in this two-dimensional space can be expanded in terms of sz plus and sz minus. Okay, there's another thing going on here. We know that this sz plus and sz minus are in a sense orthogonal. All right, we'll define these things more clearly. These are orthogonal. Okay, what do we mean by that? We talked about x hat and y hat. Okay, these are orthogonal. When we say that these are orthogonal, this means that the vector x hat has no component along the y direction. It has no component along the y direction. Now we saw this here, right? If the state of atoms or if the state of the atoms is given by get sz plus, these are characterized by spin value plus h cross by 2 along the z direction. Okay. Now if you send this to an SGZ hat apparatus, SGZ hat apparatus, you see that you get only output you only get output as SZ plus atoms. There is nothing here. There's nothing here. This means that if this is the state, it has no component along SZ minus. This has no component along this direction. So in a sense, these are orthogonal states. So in a sense, you can consider this as orthogonal states. Okay. Now, what happens if you pass this through an SG X hat apparatus? Okay, let's pass this through an SG X hat apparatus. All right, and we saw that it would be, you'll get two outputs again corresponding to SX plus and SX minus. This was the experiment that we carried out earlier. Okay, now if I block this, okay, and again pass this through an SGZ hat apparatus, you see that you get SZ plus and SZ minus atoms. What does this mean? This means that the Sx plus atoms have components along Sz plus direction and Sz minus direction. Right? So these atoms, this means that mathematically we can write Sx plus is equal to, okay, we fixed this these numbers by looking at the analogy 1 by root 2 Sz plus 1 by root 2 Sz minus. Okay, what we have done here is that we have taken a particular state and expanded it in terms of a set of base vectors for the two-dimensional vector space. This is what we have done here, right? So we see that Sx plus has a particular component along Sz plus, Sx plus has a component along Sz minus also, right? But Sz plus has no component along Sz minus and vice versa. So these are basically, this will be called as a set of orthogonal base vectors. Okay. All right. In the same way, we know that this is not unique. Right? We know that this base is not unique. So instead of choosing the eigenkets of Sz, okay, here we have chosen the eigenkets of Sz as base vectors. Okay. Now you could choose the eigenkets of Sx as base vectors also. This also we have seen. If you have a state Sz plus, okay, we can write it as, there are some coefficients here, I don't remember exactly, so let me write C1 Sx plus C2 Sx minus. Okay, this means that Sz plus has a component along Sx plus direction and Sx minus direction. This again means that if I subject an Sz plus beam here, a beam characterized by Sz plus spin, into an Sg X hat apparatus, I get both Sx plus and Sx minus spins. Okay, this means that Sz plus has a component along Sx plus and along Sx minus, right? But if I take Sx plus beam, a set of atoms characterized by a particular spin Sx plus, and if I subject it to Sgx hat apparatus, what do we get? We get only one output. We get only Sx plus beams. There are no Sx minus beams. Okay, this means that Sx plus has no component along. We can say that Sx plus has no component along Sx minus. In other words, these are orthogonal. These are mutually orthogonal. Right? Now, all these things will make more concrete, will explain how we can define uh, orthogonal vectors. So, right, in the case of real vector space, we say that if x hat dot y hat is 0, they are orthogonal. This is fine. Similarly, we'll generalize. All right, we'll generalize this to the case of complex vector space. We'll define some sort of scalar product or an inner product in the same manner. Okay, and if the inner product is 0, we'll say that these are orthogonal. Right? So maybe I'll just get ahead a little bit and I'll give you the expression for that. Okay, there's a nice expression, nice way in which you can represent this scalar product or inner product in quantum mechanics, especially in the Dirac notation. All right. So we said that the states Sz plus and Sz minus are orthogonal. So orthogonal. All right. In quantum mechanics, we'll denote it like this: Sz plus. This is equal to 0. Okay. This is how we'll define an inner product using the Dirac notation. Okay, now this object is slightly different from this object. This will be called a bra. This we already called a ket. Okay, now this together reads as bracket. If you put a c in between, this reads as a bracket. So together this is a bracket. Okay, so this is why Dirac actually named this as bra and ket, because they form part of a bracket according to Dirac. Right? So bracket gives you a scalar quantity, a number, a complex number in general. Yes, this is I'll make these things explicit, all right? So this is these are objects in a dual space basically. These are objects in a dual space called the bra space. We already discussed the ket space, the space of all kets. We also have the space of all bras, etc. These are basically dual vector space. We have seen the concept of duality in previous, maybe in some of the previous classes, okay, in classical mechanics or in electrodynamics. Whenever we deal with vectors, we talk about some sort of duality. Okay. Now, don't worry about these things. Okay, I'll make these things clear as we move on. Okay. This is I'll just give you the reason why we call this as kets. Okay, a ket is actually a part of a bracket, and there's another part called a bra, and together they form a bracket, and a bracket is synonymous with the scalar quantity. Okay, now this is how we'll denote scalar products, and this is how. So just as we say that if x hat dot y hat is 0, they are orthogonal. In the same way, if the bracket of sz plus and sz minus 0, we say that they are orthogonal. Right? So this is how we'll denote the inner products, and these things I'll explain in detail in the next class. Okay. Now, if you are studying quantum mechanics for the first time, all these might seem a little bit arbitrary, right? There are certain rules we didn't give really good reasons to choose these as the rules, okay? So all this might seem a bit arbitrary, even if we are pretending to develop it based on the result of Stern-Gerlach experiments, okay? So we are pretending that we are developing all this based on the Stern-Gerlach experiments. But okay, based on the Stern-Gerlach experiment, we can talk about vectors to represent states, etc. But then observable to represent operators, this seems more abstract and more arbitrary. All right? Now, there is no surprise if you are a little bit confused and if you are a little bit disappointed at this moment. The reason is that quantum mechanics was actually developed by the work of a lot of really smart people. All right? Over many years, it took people, the smartest people in the world, it took many years to develop this quantum mechanics, and they didn't understand exactly what was going on. They were trying different types of mathematical frameworks, and things got difficult. They had a tough time developing quantum mechanics. All right. Now, what we provide here is only the final result of all these things in a concise and beautiful manner, right? What we call as the Dirac notation. Okay. Now, or the Dirac formulation of quantum mechanics. All right. So we are giving this all these results or all the theory in a concise form. In the end, we will have a set of rules. Okay. So once we complete the mathematical formalism, what we will have is a set of rules using which we can make correct predictions. All right. Now, ultimately, the reason why we accept this mathematical framework is, one reason is that it's logically consistent. Okay, we are using mathematics, and logic is built into mathematics. So our mathematical framework will be logically consistent, and that's a good argument. All right. But the most important argument is that it makes correct predictions about nature. Okay, so quantum mechanics, the mathematical formalism called quantum mechanics, makes exact predictions exact predictions how the uh, regarding how the microscopic world behaves. Right? So this is why we accept it. Right? It works. This mathematical framework actually works. Right? Now, before it all, basically, in the end, all right, what you should do is that you should remember these rules. You just have to remember the rules. Okay, some of the rules we have given. Okay, states are vectors. Okay, I should put an arrow to both sides. If states are vectors, then vectors are also states. Okay, if you have a vector space, every vector in that particular space is a possible physical state. Similarly, observables are operators. Right? Measured values are eigenvalues of these observables, and this vector space, we said that it can be related to the span of the eigenvectors or eigenkets of the observable under question. Okay, these are basically the rules. We'll repeat some of these things as we move on. So if you find it difficult to grasp all these things at the moment, don't worry. Okay, things will become clearer as we move on. Once we set down the rules in a very clear manner, these things will become clearer. All right. So the important thing is the important thing that we are doing here is that we are getting familiar with the mathematical formalism. Once we understand the mathematical formalism, these things will become much easier. All right. Then you will see that quantum mechanics is actually easier than classical mechanics. All right. It may seem confusing at the moment, but you will realize that these things are easier than classical mechanics because we are basically using linear algebra only. Okay. All right. Now, as far as the mathematical framework is concerned, I would like to give you an assignment. We talked about complex vector space, linear vector space, etc. We didn't give the exact definition for these things. All right? We are pretending to develop it based on the experiments. But as an assignment, I ask you to check some mathematical physics textbook or even some quantum mechanics textbook and give the axioms that define a linear vector space. So the linear vector space is actually defined based on certain axioms. All right, so I'm asking you to write down the axioms of linear vector space. All right, there may be a number of axioms, like 10 axioms, which are easy to understand. Right, one of them is the closure property. The idea is that this we have already seen. If you add two vectors, you'll get another vector. Right? It does not take you out of the space. You get another vector in the same space. Okay. So as an assignment, please write down the axioms that define a linear vector space by looking at a mathematical physics textbook or even some quantum mechanics textbook. All right. I ask you to do this because these axioms are not given explicitly in the textbook that we are following. All right. We are following the textbook by Sakurai, and these axioms or the definition of linear vector space is not given explicitly. Okay. It may be useful to look at the definition of the linear vector space, okay, from a mathematical view.